Good morning. My name is Grant Kramer, and I am a professor emeritus of the University of Nevada, Reno. For over 30 years now, I've been lecturing on science and science subjects, as well as introducing in my lectures the scientific method. This is a very important video, and I hope that you will stick through the entire thing because every aspect of it is very, very important to the basis of our science today and the scientific method. The scientific method is at the very heart of modern science and is used to explain and predict the physical and material world around us. Francis Bacon, who lived from 1561 to 1626, is often described as the father of the scientific method. Over the years, this method was refined by philosophers of science into the classical scientific method, as exemplified by Darwin, who lived from 1809 to 1882, and was described by Kramer, not related to me, in 1896. The following are excerpts from Frank Kramer's book, The Method of Darwin, a study in the scientific method, published by A.C. McClurg and Company in Chicago in 1896. These are excerpts from the pages 25 through 46. The inductive method, note this is the modern scientific method that he's referring to, consists in the formation of an hypothesis from the facts by induction at the earliest possible moment in an investigation. Deductive application of the hypothesis to known facts and in the search for others that ought to exist if it is true until it proves itself imperfect. By the help of new facts, the hypothesis is improved by induction and again applied until by successive approximations it reaches the truth. The scientific or inductive method, as understood and practiced by Darwin, begins and ends with the facts. It takes nothing for granted that relates to the matter under investigation and assumes as true only such things as the law of causation and the validity of the reasoning processes. In the scientific method, the object is not merely to deduce consequences from the laws or principles, but to establish the truth or falsity of those laws or principles themselves. Hence, there's an incessant interplay of induction and deduction. The truth is, Darwin trusted nothing. Induction furnished him hypotheses, and deduction interpreted known facts and led to new ones under those hypotheses. But verification of his deductions was as indispensable to him as sunshine to a plant. Thus, the modern scientific method starts with facts, observations, and is followed by induction, hypothesis, deduction, verification, induction, hypothesis, deduction, verification, and so on. It is a continual process of successive approximations. Induction is going from the specific to the general. Deduction is going from the general to the specific. For example, in math, if we assume that a theorem is true, then we can deduce certain things from it. In science, we have to be careful of our assumptions and realize that they give us a framework to work on, but future evidence may give us reason to adjust them or even to abandon them. The scientific method has 5 steps. 1, observe some aspect of the universe. That is, observation is followed by induction, where we invent a tentative description or explanation called a hypothesis that is consistent with what we have observed. 3, we use this hypothesis to make predictions. That's deduction. And 4, we test those predictions by experiments or further observations. And 5, we modify or retest the hypothesis by repeating steps 3 and 4. Note that some people add a question as a separate step before the hypothesis. A scientific hypothesis is the taking of facts, observations, and composing an untested explanation for what we think is the cause of our observations. A hypothesis must be empirically testable and falsifiable, or it is not a valid scientific hypothesis. For example, we might observe that grapevines grow better in Reno than in Fallon. We might also observe that Fallon has salt crusts on the soil, and Reno does not. In addition, we know from past experience and the scientific literature that most land plants do not grow well in seawater. We then compose a hypothesis. Saline soils cause the inhibition of growth of grapevines in Fallon. An example of an invalid hypothesis, not empirically testable or falsifiable, would be, the strange happenings in my house are caused by ghosts which disappear and are undetectable every time someone is present or tries to detect them. Even if this is true, it is not testable. So how do we test a scientific hypothesis? How do we determine that it is verified? A hypothesis leads to a prediction. A prediction can then be tested. When testing a scientific hypothesis, the results will support or not support the prediction, yes or no. Specifically, we test the null hypothesis. The null hypothesis is the opposite of your prediction. For example, you may predict that salinity causes a growth inhibition in grapevines. The null hypothesis would state that salinity does not inhibit the growth of grapevines. You would then proceed to conduct an experiment where you would apply salinity, the treatment, to some grapevines and not apply salinity to other grapevines, the controls, and then measure the growth of the grapevines. A valid scientific experiment must have at least one control. To determine if our experimental results support our hypothesis, we must use statistics. To use statistics, one must have replicates. That is, one must repeat the experiment or the measurements. Then one can apply statistics to determine if the results are significantly different from each other by testing the null hypothesis. In other words, there is a high enough probability that they are different. The level of confidence is usually set at 95%. This means that you are 95% sure that these results are accurate. Note, there is a 5% probability that your results are wrong due to random, as I'll explain in a minute, or experimental errors. This is why experiments must be repeated a number of times to increase the probability that our conclusions are correct. Generally, when statistics indicate that there is a 95% or higher chance that our hypothesis is correct, we consider that our hypothesis has been verified, that the results are significant. If we have 99% confidence or higher, then we say we have highly significant results. Note, you can never prove a hypothesis. You can only disprove one. For example, the inhibition of growth of the grapevines that we spoke about earlier might actually be caused by cold or insects or disease or something else that we haven't accounted for. Another reason for never being 100% sure involves chance. When one flips an honest coin, it is possible that you could get 10 heads in a row. However, the probability of this happening is very low. There's a 50% chance that one would get a head. Therefore, the probability of getting 10 heads in a row is 0.5 to the 10th power, or 1 in 1,000. Very small, but still possible. Thus, it is possible to conclude falsely that our coin is biased when the truth is it is not. This leads to the notion that even after a hypothesis is supported by a set of data, it is still not considered sufficient to prove that the hypothesis is the truth. Scientific theories or laws are like hypotheses. but are much stronger explanations or descriptions of certain phenomena. They are based upon a hypothesis or a group of related hypotheses, which have been confirmed through many experimental tests. Once accepted, theories are not easily discarded. One usually tries to fit results within the accepted theoretical framework. If it does not fit within this framework, then many experiments must be performed. If the results are consistent, then the theory may need to be modified or even abandoned. Clearly, the colloquialism, "it's only a theory," which infers a very speculative nature, is at the opposite end of the confidence spectrum from a scientific theory. This is one of my pet peeves that I always hear on the news or amongst other people that are just talking, "It's only a theory." Well, in science, a theory is much more substantive than a hypothesis. What they mean to say is it's only a hypothesis. But the expression goes on, and I will continue to object. Now, there are limits to the scientific method. One of the most important limits is that one cannot repeat a single event only. For example, the beginning of the universe. Bear in mind then that the scientific method is a very useful method for allowing us to predict our environment around us and allow us to be able to understand what might happen in the future. But it is a probability, it is a prediction. It cannot explain everything. Well, that's it. I hope you've enjoyed this video and have deeper insights into the scientific method. Have a great day.